let me introduce the third, the last but not least speaker for our mini-series associated with our anniversary. So Valerio Scarani is someone who probably doesn't need that much of introduction. Although he's Italian, most of his education is actually Switzerland-based. He got his first degree and his PhD from Lausanne, and then he moved on to Geneva, where he was a postdoc. And then we were very lucky to capture Valerio and persuade him that there are better places than Geneva, and then here he is in Singapore with us. And Valerio worked on many aspects of physics, and he's known for many contributions to quantum optics and also quantum cryptography. He's known for his security proofs. He's also known for his... basically, he was one of the co-discoverers of device-independent methods in cryptography. And without any further ado, I will let Valerio to take the floor. I was reminded, though, by Yvonne to mention publicly that the coffee you are drinking is sponsored by Spinelli. And there's another nice announcement. I'll leave it to Valerio about our colleague who ventured into artistic world. But Valerio, I'll let you do all the honors.
Well, I don't see Dagomir, but I think we have to congratulate him for a movie award that he just got. You can get all the information from the CQT webpage and start watching his movie, the prized one, and a few others. Okay, I'll try to be short, and a difference with the other speakers is that probably I will not mention any of my research results in this talk. It will be more like just like a big framework. Many things are trivial, I announce it, and a few probably are not, or at least are trivial. I think everything is trivial once you think about it. But sometimes, even myself, 1 year ago, I would have said many stupid things about this topic, and it's only by thinking and discussing with people and getting criticized that I realized, hey, maybe I should be more careful in these things. So this randomness is about unpredictability. So I want to start with a statement that unpredictability is normally related to insecurity in our lives. And it's something very strange, because, for instance, if you look at let's say, some economic crisis, there's always a nice exercise of people to try to find out, why we have not been told before. It was obvious that it was going to happen. And it's not only the end investors that have no clue of what's going on. Even some people heavily involved in the process, lost money. So somehow there's something strange there. Even when science cannot give you some information, this happened in, earthquakes are very tragic events. We cannot predict them yet, but still the Italian justice managed to convict 7 scientists for not having warned the population. This is something that happened in my country. So anyway, whenever there is this kind of problem, we know it's difficult to accept that something is really unpredictable. We think, well, where are the experts? What are the experts doing? Now, it's also true that we tend to blame the experts or even God for things that we are not able to predict and so on, but we all believe that there is something really unpredictable. And we believe it every day. We do believe that our passwords are unpredictable, otherwise we wouldn't use them. Of course, it depends up to which point you do believe this statement. Okay? But somehow there is something there, that there is a trade-off between what I can predict, and this shows you that sometimes unpredictability can be good. So I have a slide on cryptography. I have to mention that I did some cryptography before, and I think cryptography can be summarized in one slide, which is, well, this one. And random for me is bad, random for the others is good. So if I have something that I cannot predict, it's a problem. If I have something that the others cannot predict, but I can, and maybe my friends can, then this is secrecy, and this is something, these are resources. So that's somehow one of the main messages here. Now, in this talk I'm going to speak about physics. And when you speak about physics in these terms of randomness, there is the famous unavoidable quotation by Laplace about physical determinism that I show here. So I read it in full. We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect, sometimes called the Laplace demon or the Laplace intelligence, which at certain moment would know all forces that set nature in motion and all position of all items in which it is composed, if this intellect were also vast enough to submit this data to analysis. Remember, he has written in French. We Southern Europeans like, you know, long sentences. Anyway, so if this intellect was submitted to, it would embrace in a single formula the movements. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. This was written, in fact, in one of the first systematic treatises, not on physics, but on probability theory. The theorem of the probability. Very well. So that's the famous citation. And now, as we all know, probably, in the 20th century, something happened with this sentence. Two things happened, in fact. I just want to highlight these two blocks. One thing that happened is that, yeah, Laplace noticed very well that indeed this thing, if the intellect were vast enough to submit this data to analysis, is impossible in practice, because we have finite computational resources. And this is the case, for instance, of deterministic chaos that can be for complex systems like the weather. I'll have a couple of more examples later, or even simple systems but with complex nonlinear dynamics. That's one of the parts. What maybe was more unexpected would have been more unexpected to Laplace is that the other part is also wrong. And this is because of quantum physics. It's impossible in principle to know, well, maybe not all the forces, but all the momenta and the positions at given time. So where are we now? Because we started with earthquakes and so on, then we went to, we are there. So I said that randomness means unpredictability. And unpredictability, if you open a book on unpredictability, there are quite a few, the popular ones and so on. And then you get all kinds of things, notably on this side. Like people like to write things about stock markets and polls and crowds, and then they want to show the statistics are very useful. So normally the Americans speak about baseball. Apparently in baseball, if you look at the statistics of the players, you can buy the right players and then put up your team or something like that. And also, of course, it's fantastic, unpredictable how an individual works. Well, you probably know it from your relationships. Unfortunately, more important for society is probably criminal behavior, and terrorism, of course, is one of the typical things that people want to discuss in this context. And the famous topic of free will, by the way, ends up here. So as you know, it's not in my line. My line is down there. And here, the one that I say not involving humans, well, there is this computational unpredictability, again, complex systems, simple but chaotic. Even pseudo-randomness can be put here. So pseudo-randomness, as you may know, is algorithmic randomness, where in fact, you just, let's say, push a button at a given time, and it's the time at which you push the button that determines, is a seed for a deterministic algorithm that inputs something, outputs something that is sort of hard to predict if you cannot decide, monitor very precisely at what time you push the button. So all our randomness in the computers use this. And then there is this famous claim that I just made that there is sort of intrinsic randomness in quantum phenomena. And now I'm going to focus on this line. So, because the quantum claim is very strong. I don't know, I mean, here, because I see many of my colleagues and friends, so, well, you know this thing. Maybe there are other people who are not very familiar with that. So my old question is this. So are we sure that there is something really intrinsically unpredictable in nature? These are some cartoons of some philosophers. I have to admit I would not be able to recognize all of them. There's certainly Socrates here, Nietzsche here, Marx here, probably Russell, and probably Kant. The other three, well, I have to figure it out at some point. So that's a question that we may receive. I mean, as physicists, we may be asked, hey, come on, you know, are you really sure? Yeah, physics is very predictive. It's a fantastic thing. So are you really sure that there is intrinsic randomness? It's a bit of an outlandish claim. And then there is another claim that is, well, you know, there are some people who just don't care. Yeah, sure, okay, there is intrinsic randomness. Why not? But then does it mean that quantum devices are better at generating randomness than classical devices like this one or that one? And that's a question that I received quite often. And I remember, for instance, when Antonio Athin came a few years ago to give the colloquium here in CQT, for those who were here, well, he was not very careful with his statements, and then especially Dagomir, you know, went for him, no, and said, hey, come on, I mean, the randomness is also classical, no, not only quantum, so why are we making all this fuss? In the meantime, as you know, we got a grant for that, so it's better try to find a reason for why quantum randomness is useful. Now, let's go a bit of history, the timeline of these claims of randomness. So when did it happen that people started speaking of randomness in quantum mechanics? I think, well, probably the safest point to start is when Max Born, not exactly 1926, he started in 1925, continued 1927, kind of around 1926, which is, by the way, the same year as the Schrödinger equation and the matrix mechanics of Heisenberg, so the same year of quantum theory properly established. He proposes a probabilistic interpretation of the wave function, and he receives a polite letter from Einstein where he puts the famous sentence that he, meaning God or the old one, doesn't throw dice. But this interpretation is rapidly endorsed by Bohr and many others and becomes the orthodox interpretation. As you certainly know, Einstein and Schrödinger will continue struggling, a few others continue struggling against that. In 1927, another manifestation of randomness is the Heisenberg uncertainty relations. And I put the relations with a smiley because, yeah, it's nice, and a microscope with a sad face because I mean, the model that Heisenberg came up to explain the uncertainty relation is unfortunately flawed. So he tried to explain the uncertainty relation in a classical way, and by doing that, he introduced some misunderstanding there that is perpetuating in some textbooks till now. Then John von Neumann in 1932 tried to really make sure that there is randomness, and he came up with a no-go theorem for hidden variables, unfortunately also flawed for some technical reason. In 1935, there are these two famous, I would say the latest attempts, probably, maybe Berger can correct me, maybe there are some other attempts later, but the latest attempts of the big founding fathers to show that quantum physics is problematic, and this, especially this randomness feature or some of the strange features should be corrected. The famous Nancy-Podolsky-Rosen paper and the paper in which Schrödinger describes this metaphor of the cat, saying that it should be absurd to consider a cat dead and alive at the same time. The thing goes on for some time, but essentially the next big result is probably the one of John Bell that I'm going to describe later. Before that, I just want to mention two things that I don't agree with, but I have to mention because I will mention them later. Around the 1950s, there are two sort of interpretations of quantum physics that try to recover determinism. And one is what is called Bohmian mechanics with a sort of pilot wave. If you don't know what it is, it's not a problem. You can Google it later. And then the relative state of Hugh Everett, later called many worlds, also appear in those years. So now you have a lot of, I think in this timeline, for the purpose of this talk, you have a sort of historical milestones of, so it's safe to say that these people believe that in a way or another they could restore determinism into quantum physics. So they found a way, if you want to go around this claim. Okay, so how do we certify now intrinsic randomness? I told you that we want to convince our friends that we are not making outlandish claims, we are just doing serious claims. But you may know who these guys are. This is the famous painting of Raphael. This is Plato and Aristotle. Plato pointing to the ideas, Aristotle showing that we have to observation is important. Okay, so how do we certify intrinsic randomness? So this is my random number generator. Black box, spitting stuff. And then what random means, it means that this list, or let's say the next bit, is unpredictable for someone or something. Well, ideally, when you say random without saying for whom, is a big mistake, but ideally means unpredictable for everyone else. Or everyone that is not reading the thing. So it means I kept this list, and then I have this list, nobody else can know anything about it. So how do you check that if it's random? The typical way to do it is to run statistical tests. There are many of these tests. The NIST has a battery of tests. You can run them, and then so you check essentially correlations. No, if you don't know what a statistical test is, well, first of all, you would check that there are roughly as many zeros and ones. Then maybe you check that there are as many 0, 0 as 0, 1 as 1, 0 as 1, 1. And you do this a little bit for a few longer sequences because it becomes a bit cumbersome. And then you start checking correlations and other things, and run all these things. And then if you pass the test, you can say, oh, it's random. which is fine. But there is something. And this is probably, when it comes to quantum randomness, this is probably the main difference. Is that even if this random number generator passes all statistical tests, it could have been pre-recorded. And why it could have been pre-recorded? Well, it's a trivial statement. Imagine that you have the real random number generator, you generate real random numbers, really, really random, you burn a DVD, and you give me a device that contains the DVD with the sequence you produced. Well, this sequence will pass all the statistical tests, because it's identical to the one of your real random number generator, but you have a copy. So suddenly it's not random for you. It may be random for anybody else, but not for you. So in case of secrecy, that may be a bit of a problem. And one of the main features of quantum randomness is we can do black box certification that the sequence is not pre-recorded. And that's ultimately what I'm going to call intrinsic randomness, although I think that Max Born was right. I don't need to go for Bell inequalities for that. Anyway, in order to do this certification, you need to complicate a little bit the device. So I cannot have just this box, single box fitting numbers. I need two boxes, and these two boxes must have an input, not only an output. So this will be the output. Now, for convenience of physicists, I will label my bit +1 and -1 instead of 0 and 1 as before, but that's the same output as I had before the 0 and 1 list. But I need an input. An input is a knob or a button on the box that I can choose to push. I can have two buttons. For instance, here I have two buttons, 0 and 1. And I can choose to push one button or the other. And I do it. And then the other person here does the same. We can discuss later whether I have to do it really with my own whatever free will or whatever it is. That doesn't matter. Really doesn't matter. But okay. A famous physicist has spread a lot of misconceptions about what is needed as a resource here. If someone is interested, I can tell you later. Otherwise, wait for a Stefano Pironio draft soon on the archive. So, what would be the pre-established agreement? What means that the things are pre-recorded? It means inside here, there is a list of instructions that says, the first call, the first use of the machine. If the user pushes the button 0, output +1. If the user pushes the button 1, also output +1. Second call, if the user pushes the button 0, output -1, and if the user pushes the button 1, output +1, and so on. Similarly, on the other side, a similar sheet. And moreover, I can allow these two sheets, as Aram said before, this could have been pre-agreed, pre-established. So I can allow the machine inside this box to have knowledge of the list of the other machine. That's why there is this thing here. So what can you do with that? Yeah. Well, this is something you can do. So please, physicists, including Jenny, never more write that entanglement means that when I do the same thing, I get the same thing out. Because that's trivial. Every person that has a brain turned on, unfortunately in today's world is a very small subset, but every person that has a brain turned on can check that this can be done without quantum entanglement. So every time we write these, we are just, in my opinion at least, cheating. And if someone thinks, this is nonsense, what these physicists are saying. Why? Well, look at here. I mean, here, Alice and Bob have the same instructions. Okay, so each time they do the same thing, for instance, x = 0, y = 0, and they get the same outcome. Not particularly astonishing. In real life, you can have, just an example of stock exchange, Imagine that there are, in different stock exchanges in the world, a company decides that if the Republican Party wins the elections, you sell. If the Democrat Party wins the election, you win, you buy, Okay, then there are all the brokers there waiting for the result of the election. When the information comes, they all simultaneously, at a distance, act in the same way. Any mystery? No. Any entanglement? No. They had the instructions. They knew what to do. Okay, so that's something you can do easily with pre-established agreement. And this is something you cannot do, however, and this is also something that is related to the CHSH game. It's the same game, in fact, that Aram was speaking about. I cannot win if the goal is to output the same output unless both users have chosen the input 1. Why? Okay, let's suppose that this box has already a determined strategy. Then here, you see, when this box receives the input 1, it doesn't know what to do. Because if the other box had the input 0, then it should be the same result, so this should be +1. If the other box had the input 1, these should be different results. It will be -1. So if I want to win this game now, there must be some information traveling from here to there. Or from here to there. Of course, it's symmetric. Bob should know the input of Alice. So classically, this can be done, of course, by signaling, sending a message. And the interesting thing is that quantum physics does it without sending a message. But before doing that, I want to show you probably the minimal interpretation of these criteria, which is, so suppose you see these. You have two black boxes, you run your thing, and it works. What do you conclude? Well, the necessary conclusion is that at least one of the outcomes was not pre-established. Okay, that's the basic conclusion from this reasoning. You can now try to find why, what's going on, but that's a different matter. So the classical inference, you would say, aha, then one of the boxes is sending a signal to the other. Now, in quantum mechanics, and also, well, we can arrange situations with space-like separation in such a way that no signal can have been sent. And that's the interesting fact, no? That the quantum statistics predict that two quantum particles sent far away from each other can do that, or not exactly that, close to that, without signaling. Okay. But that's my main point. So if you see a behavior of this type, you have to conclude that at least one of the outcomes was not pre-established. So we can certify randomness. Okay, so here is the proof of Bell inequality well, so you have probably, many of you have seen these, but just for those who have not seen it to see that it's not a difficult theorem. Then you can discuss about subtleties, about definitions and so on, but that's not the way we prove this theorem nowadays, by the way. That's a sort of pedestrian way of doing it. So how to do it in just one slide, huh? So it will be finished here. So these are my pre-established results. For each run, the two boxes know what to give in case the input is 0, in case the input is 1. That's the second box. Then in this case, you can define this number. And this number, if you look carefully, is either +2 or -2, because if these two are equal, this is +or -2, and this is 0, +or -1. And if these two are different, are opposite, this is 0, and this is +or -2. Then you go through a trivial, second trivial argument, which is the following, that, you see, before I told you that you can push only one button each time, so you cannot really measure this guy all the time, but you could measure, for instance, 0, 0. Each time both of them have pushed a 0, what came out of the boxes? Each time Alice pushed a 0, Bob pushed Alice pushed the button 0, Bob pushed the button 1, what came out, and so on. And the average, well, the average of a sum is the sum of the averages, and so this average can be computed, can be measured, this average can be measured, this average can be measured. And now if I put these two together, well, the average must be smaller than 2, because at most this number here is at most +2, and you cannot, by adding numbers that are smaller than 2, go above 2. And so if one observes now that S is larger than 2, what can be wrong? Well, probably not here. Probably not this mathematical inference. So probably the only thing that can be wrong is that these numbers did not pre-exist. At least not yeah. At least one of those did not pre-exist. And the fact of making a measurement sort of influences or has some statistical influence on the other, not a direct influence. Okay, so that's the pedestrian proof. Okay, so where do we stand now? Okay, before Bell, there was, of course, already a very, very strong evidence of randomness. And in fact, most physicists would speak of, the sentence, quantum physics gives you only statistical information and not information on the individual results and so on. This sentence has been around for a long time. We didn't have to wait for Bell to say that. But somehow was theory dependent. For instance, the Heisenberg-uncertainty relations, well, is something that requires you to write down commutators, to know what a state is, what the dimension of the Hilbert space is. Now, okay, 1964 is when John Bell reported his ideas, and the example I gave, in fact, is not the one of Bell because there was an additional assumption that he left in, so the proof I gave is the one Clausen-Hahn-Shimonian hold. Quantum theory predicts a violation. That's already pretty lucky. You know, a priori, there's nothing that says that if you have intrinsic randomness, you must violate a Bell inequality. You could have intrinsic randomness and without entanglement at all. That's for me one of the things that I still don't understand in the foundations of quantum physics, understand in the sense of why do we have to have entanglement? It doesn't follow from randomness, at least not directly. But thanks God, quantum theory predicts a violation, so it can be tested. And when it was tested, well, we all know that the violation of this inequality was reported many, many times, beyond scientific doubt. There are still some loopholes to be closed, but okay, we can discuss about these. Well, there is some reason to do that. Not only to publish papers in Nature, which is certainly the main reason for some of the groups. Okay, now I have 3 slides on how we do things nowadays, just for you to have an idea of these tools that we're using nowadays. So this is the kind of thing that Stefano Pironio and other people, including Jean-Daniel, my postdoc here sitting there, like to write down. So this is the quantity you want to compute, is the maximum over all the probabilities subject to a few constraints. And then this one is a bit tough to do, so you do semi-definite programming to relax it. But I will not even mention semi-definite programming here. I just want to tell you what is the local polytope, okay? Because I think that's an interesting thing. So here is one of my deterministic pre-established agreement points. Those that do not violate any Bell inequality, so all plus. And here's another one. What's the difference? Well, in this case, when Bob pushes the button 1, the outcome will be minus instead of plus. Now, in whichever space I'm drawing these points, you can probably rapidly see that I can draw a line between them. And what is this line? Well, it contains all the statistical mixtures in which, for instance, if I draw the line between these two, well, A0, A1, and B0 are always plus. And here I'm closer to this one, so let's say that I have 70% probability of getting minus and 30% probability of getting plus. Clearly, this can be done. I can just choose 30% of the time this box, 70% of the time that box, that strategy. Okay, so that's clear. And now you see probably what I'm going to do. Now I'm going to write another point, and also the other lines they define are perfectly defined. And then I can put a 4th point. Now this 4th point is probably not in the same plane, so it will go out and form a simplex. And then, well, there are 16 of them. So now the drawing is going to be messy. The final outcome is that the whole thing will define a sort of cube or a tetrahedron or whatever you want to imagine. Anyway, the distances don't really matter. What matters is the connection in an 8-dimensional space. Hard to imagine, but what is important is that all the observation compatible with pre-recording are inside. So now I have a geometric view of what is a Bell inequality, or what are the objects that I'm trying to rule out. The pre-established agreement are inside this cube at 8-dimensional. So here is my local polytope now is 8-dimensional. Polytope, by the way, polytope is a technical word for a convex set with finitely many extremal points. So a convex set is a set such that if you take 2 points and you draw the line, the whole line is within the set. Okay, counterexample, a donut, or like a airplane pillow. That's not a convex set. And then the quantum set is not a polytope because it's also convex, but it has infinitely many extremal points. The quantum set is what you can do with measuring quantum states of arbitrary dimensions. So here is not qubits. There exists some quantum state and some measurement such that I can get these probability points. In fact, Jean-Daniel may correct me, but I think it's proved that if you restrict to qubits, the set is not convex. Yeah, he confirms. It was an open problem for some time. So if you restrict the dimension of your Hilbert space, the quantum set is not convex, but it becomes convex if you allow all possible extensions. Okay, so So that's my famous Bell inequality now. Remember that I had the inequality S smaller than 2 for pre-established agreement. So this facet, this hyperplane, is a flat surface, is going to be one of my Bell inequalities. This plane is defined by S equal to 2. All that are below, well, that could be done with pre-established agreement, unless you hit the other plane, but that's just the same but reliable. And if you are above, then these ones cannot be done with pre-established agreement. So this geometric way of doing is how we do derive Bell inequalities now. The argument I gave before, where there was this number S coming from the sky, and just say, trust me that this is going to be interesting. In fact, this thing, if you take my famous lecture notes that I was giving till last year, and Dagomir is going to teach this module soon, you will find that it's sort of easy in 2 pages to compute this thing. After that, you go to computers, if you want to go a more complicated scenario. So there are some randomness there. There is more randomness up there. Aram hinted to it by saying, oh, you know, the more I have my probability of winning this for some 3/4. Oh, by the way, I should have said that this equal to 2 is the same as the 3/4 that Aram had. Exactly the same. It's just a relabeling. So if you reshuffle the whole thing into a probability of winning the CHSH game, that's the 3/4 that he had. And this would be the 0.85 that he was mentioning as a quantum limit. Okay, that's okay, no? Because you're far away from the quantum, so from the classical set, so probably you get more randomness out there. What is maybe less obvious is that you have even more randomness if you're at the same level, but on the boundary. And the reason, hand-waving reason, is that this one can be done with a mixed state, this one can only be done with a pure state. That's the kind of reasoning there. Yep. So how do you get these things? Well, the local set, the local polytope, can be obtained with linear program. You just have to list the extremal points and tell a linear program, find the planes, the extremal planes that bound this set. And at some point it finds it. However, there's no closed characterization for the quantum set. This is an interesting maybe remark for those of you. I can tell you later why and what's the problem. But fortunately enough, it can be approximated from outside. So there are some semi-definite programming, some easy-to-solve programs that define sets that are slightly larger than the quantum set. So of course, if you now compute how much randomness you can have, assuming that the resources can be slightly larger, well then, what constraints are put by assuming that the set is slightly larger, then in particular this will be valid if you restrict to the quantum set. That's how we normally compute the things. So what I've written here, well, something about randomness, finally. So what can we conclude? And then after that I will come to the conclusion of the talk. So we can conclude that if a setup violates Bell inequalities before the experiment, the results were really not there. So before the experiments, the outcomes are unpredictable for everyone. Remember that the title of my talk is random for whom? So for everyone. After the experiment, the outcomes are unpredictable for all those who have not seen them. Of course, the experimentalists who are there in the lab seeing the results, well, they've seen them. So it's no longer random for them. You still need, for instance, to make sure that there's no spy in your lab if you want to use this thing for security. Quantum physics does not protect you against corruption. It doesn't. It's clear. But normally we trust the experimentalists, so we work under the trusted provider assumption. So which means Christian is a safe person, and all his students also are. And then also Zeilinger group is also very trusted. All these guys, we trust all of them. Otherwise, we're going to problem with the theory. And maybe remember that this Bell inequality is also a quantitative criterion. So we can tell how much randomness can be certified. Not only, oh yeah, there is some randomness. But we can say how much. And then it's a matter of extracting it with extractors and so on. And these are the things that the computer scientists know better than I. Also, the experimentalists know a lot about extraction. In fact, they know how to extract. I mean, they get numbers at the end, which is maybe not everyone can do that. Certainly not me. Okay, so let's try to wrap up on intrinsic randomness. What does intrinsic randomness mean? Now, what is the point I want to make to finish? Is that, well, it depends where you stand. But when you go to some conference, to the kind of conference I end up sometimes in, when you mention intrinsic randomness, rather than getting excitement, you get angry birds. Why? Well, because, I know, in the many worlds interpretation, there's no intrinsic randomness. And neither with Bohmian mechanics. Incidentally, I don't know why I chose the ladybird to... I don't know any woman with Bohmian. Probably they're too smart women to be Bohmian. But anyway, if you know someone, can tell me later. Yeah, so it's true that these two interpretations somehow try to recover determinism from quantum data. Then there is what I mentioned already before, is that there is the guy who says, well, you know, anyway, classical chaos or classical unpredictability is just as good. And then there is the philosopher who doubts that maybe we are a big computer simulation of some alien race, no? So in fact, all that I'm doing is perfectly controlled by this superior race. So where do I stand there? So how can I reply to these questions? And because, especially if there are people here that give me the grant on randomness. So that's my answer. Again, random for whom? And once you address this question, then you get a bit more serenity. So why? Well, first of all, you have to ask, random for whom? Do you want randomness for a being in our universe? Yes or no? Well, you know. Now, if the answer is no, well, fair enough. Fair enough. I mean, if there is a being that is stretched across the multiverse of the many-world interpretation, then there's no randomness. For a being that would be capable of reading the pilot wave of the Bohmians, assuming that these things exist at all, there would be no randomness. But this is supposed to be invisible, undetectable. And yeah, for the robots controlling the matrix, yeah, no randomness, yeah, sure. Now, okay, assuming that you are on the other line, no, you can ask also the question, well, do you want randomness against a being in our universe with limited computational power or with unlimited computational power? If you want against unlimited computational power, we're a bit paranoid, but then yeah, only quantum systems in this sense are random. If you accept a being with limited computational power, then classical processes can also be random, provided they are happening then and there, so don't pre-record it. And quantum physics, as I tried to show you, allows for black box or device-independent certification of no pre-recording. So there is still, even in this line, there is still an advantage for quantum technologies. And I want to add one more that I think I don't have on this slide, is that sometimes we tend to think of quantum as complicated. Like, why would you go for a quantum realization when the electrical noise of a resistor or the thermal noise of a resistor would give you the same randomness? Well, maybe because a laser is not that complicated at the end of the day. Is maybe cheaper than, I don't know, is it cheaper than a resistor? No, but so same kind of price, no? And it, you know, it's very stable, it can operate so quantum doesn't need necessarily to be big and messy and complicated and expensive. So there can be still a reason to go for quantum for practical reason. It's faster, it may be cheaper, it may be more stable, and these kind of things. And I mean, a priori, you cannot discuss these things. You have to really compare the realizations. So I cannot, as a theorist in a bit abstract one, I cannot tell you which one, but you have to look, no? And if your device is cheaper and better and faster and whatever, but fair enough, you can go quantum. And then, of course, if you want black box, then you do device independent. I was told to advertise the fact that, I don't like these things, but I was asked to write a post for the blog of the Vienna guys. I mean, also the Austrian Research Center. Czesław Bruckner is managing a blog, and he told me to write something. So I wrote something about randomness. And I think they would like very much if there are comments, because this shows that their blog is read. Feel free to comment. It doesn't mean that I will reply back. Huh? Especially if for some of you, please come to my office and we discuss over coffee is much better. But if you put some comments there, the Czesław will be very happy. Anyway, just check these things. So let me finish with a collection of claims. So quantum physics does not disprove superdeterminism. Okay? Superdeterminism means, again, the theory that everything is determined from the very beginning, including, you know, everything, really everything, including what I'm saying. Quantum physics cannot prove that this is wrong. I know if it's particularly interesting as a position for your life, but also cannot guarantee randomness for a being outside our space-time. So feel free to believe that ultimately, whatever that means, everything is still determined. Feel free. Quantum physics does not forbid you from believing that, at least quantum observation. However, certainly there is intrinsic randomness in our universe in the sense that every being in our universe cannot predict the outcomes of a quantum experiment. I try to argue that this was discovered through quantum physics, but was proved independently of quantum physics, and in particular is certifiable without a detailed description of the device. So this is a famous cartoon that we show all the time. So that's the random number generator of these guys, well, yeah, with quantum mechanics we're working on it. Thank you very much.
Thank you very much, Valerio. And any question, comments, please. Can you
photon on a polarization of 45 degrees is put on a PBS, and you get either on the vertical or on the horizontal. In that diagram that you showed, where will this kind of setup land on?
So this would be among the settings that are not certifiable in a device-independent way. So it would be, from the point of view of foundations, it would be as good or as bad as a resistor. Because you need to know the physical process. You see, if you just give me this box and you tell me, oh, look, it spits zeros and ones out, you know, it could be anything. So, but if you tell me, I know, as you told me, oh, there is a polarizing beam splitter, and what I'm sending is real light, and there's not some strange other optical mode that is interfering, then I trust you, no? So similarly, if you want to do the thermal noise of a resistor, you can show me, there's a resistor here, and then the spectral function is flat, and you know, with temperature it changes linearly, and so okay, then I sort of believe it, no? So it would fall there.
So if I ask in a more general way, where does the randomness of measurement projections fall into your whole diagram? So whenever we measure, there is an inherent randomness involved inside it.
Well, I have adopted here a more operational way than that. So I don't want to commit to say whether, you know, there is a collapse of the wave function or other kind of models there. You know, that one, to be honest, I am very blur, as they say here, about these things. I don't have a definite opinion, but let's say what we can say is that in a device like the one, in a device with device independent, like Bell inequalities, there I really don't need, because it's really black box. So, you know, those statistics cannot come in any possible way if there's no signaling from a determined strategy. From the other one, I would say, well, let's look into quantum physics, and I know that this degree of freedom has only this particular capacity to channel information. If it's not in an eigenstate of that particular thing, then I know that the measurement cannot be, whether this is because there is a collapse or because whatever, that one, I'm agnostic about that.
Okay, thanks.
No questions, comments? Valerio, I was curious about your comment about Pironio and exposing some famous physicists who got it all wrong. Can you say us a few more words about it?
Okay, so let's put it like that. There are some famous people who have been claiming for many years that in order to do a Bell test, loophole-free Bell test, you need an input that is a quantum random number generator or something of this type. No? Well, I don't want to spoil the whole beauty of Stefano's arguments, no? But you know, what is important really for a Bell test is not at what time your random number generator is generated. So the image that Stefano has is the following. Suppose that you try to do, you generate your input, your own free will, whatever it is. Now you are there, and you know that to be space-like separated with the other, when the clock reaches this position, you have to think a bit, 0 or 1, no? And then choose. And now suppose that 2 seconds before this happens, your brain, you're there concentrated, I need to hear a bit, well, 0, oh shucks. What do I do now? Because this bit was available 2 seconds before I should have pushed the button. So should I change it? You see, you go into operational problems that are very stupid. What Stefano was saying is that, stressing correctly, I mean, he's not the only one who stressed that what you really need for a Bell test is that the process that chooses the inputs is uncorrelated from the source. And then, once you have this idea, then his example was the Geneva phone book. So suppose that I tell you that when here we are going to do the loophole-free Bell test, we choose the settings using the digits of the Geneva phone book, starting with the first guy there, and then, it's written already. The Geneva phone book does exist. It's not, it's in the past of everything. There is a causal cone that whatever. Now, tell me a good reason why the photon pairs that are being produced in whatever lab should be correlated with the Geneva phone book. So that's the kind of argument that Stefan is bringing up to say that you don't need a real-time generation of, as long as you convince, and I think Richard Gill is making a similar statement. I tried to do a similar statement, but was not so, I messed up when I wrote some things, I wrote it too fast and I didn't concentrate too much on making it there. There is some evidence that what you need to check is that it's insanely improbable that the process that chooses your inputs is correlated with your source. And it doesn't really matter if you choose them at time 0, at time 0 plus epsilon, a space-like separation, or whatever. That's the kind of thing.
Thank you. Last chance to ask Valerio a question here. Of course, Valerio is around, so those of you who are interested in any further discussions, Valerio is always willing to entertain visitors to his office. Is that a right statement? Okay, well, let's thank Valerio for this very illuminating talk. And I would like to take this opportunity also to thank all our speakers who came from so far away. So thank you very much for taking your time coming to Singapore to somehow celebrate it with us 7 years of our existence. So starting from this week, we are entering as a Center for Quantum Technology into the 8th year, and hopefully many new and interesting results will be produced in our labs in this forthcoming year. So this is our anniversary, which we celebrate every year. It's a special occasion. And thank you to all of you and to all the team that prepared this event. So I would like to say thank you to Yvonne, to thank Jenny, our outreach person, and basically everyone who was behind the scene, making sure that you are directed into the right lecture hall, that the coffee is there, and that we all can enjoy those wonderful 3 talks that were presented today. So thank you to all of you for your work, and thank you for coming, and hopefully those of you who show up every year, I'll see you next year. Thank you very much.